Hello, welcome to our lesson 1.2 on solving equations. So let's dive right in to discuss kind of some things that you learned in high school. In high school, you solved equations, and hopefully you talked about kind of when you're trying to solve equations, what's your overall goal? What are you trying to actually achieve? Well, let's actually write an equation down just to talk about while we look over this. Something like 4x minus 15 equals 13. So if I said solve this for x, some of you already kind of know what to do instinctually, some of you kind of remember what to do, but I want to kind of build a structure of a set of understandings to kind of stack upon so that when we get to really hard things to solve, you'll have this structure to rely on, not some gut instinct, unless the instinct is well made, and not some just I memorized how this should look, but I don't want to memorize everything. So let's give you some deeper understanding. So what's the overall goal? And most people say the overall goal is to get x by itself. X equals some number. That's the goal, right? To get x by itself, or the fancy way is to say it, to isolate x. Well then, how do we achieve this goal? Well, the way we achieve this goal is by using inverse operations, or basically undoing things, right? So I'd like to get x by itself, and you notice those are equal sign. There's two sides of the equation, and if I'd like to get x by itself, let's kick everybody else out of this side, so there's only x left. But if we're going to try to do this by inverse operations, let's kind of talk about what tools are available to us, and I want to kind of mention one very huge idea, one big fact. So I am allowed to perform any operation on the left or right that my little heart desires, and if it ends up being something that changes the value, I need to do it to the other side to keep things equal. So for instance, let's do this in an intelligent way. I have well, a minus 15 and a times 4. Now, we'll talk about order in a second, but if I wanted to get rid of this minus 15, how do I get rid of minus 15? Well, the opposite of subtracting 15 would be adding 15. Well, ask me, is that any bit valuable? Well, let's see. A negative 15 plus a positive 15, oh, that adds to 0. That'll be gone. Now, I've changed the value of this left side by increasing it by 15. So I need to make sure I do the same thing on the right side there. So I've done the same thing. I've kept this balanced. I've kept this equation truly equal. And all that's left over here would be a 4x, as negative 15 plus 15 adds to 0. And we can say it kind of goes away, or plus 0 means nothing over here for us. And 13 plus 15 is 28. So I've almost got an x by itself, but it still has this 4 with it. And once again, there's no operations shown there, but what's understood to be there? Multiplication. So how would I get rid of multiplying by 4? Well, that's simple. I can divide by 4. Because 4 divided by 4, let's see, what would 4 divided by 4 be? That'd be 1. And I would just have, if I do some thinking over the side, 4 divided by 4x. That'd be the same thing as 4 divided by 4 is 1. 1 times x. Well, do I have to show the 1 times x? 1 times x is just x. So lazily, what we often do is say, we lazily say it cancels. Some math people will really fuss at you for that terminology because it technically doesn't go away. It just divides to 1, and then we say, oh, 1 times anything is itself. But for us, we can kind of agree upon being mature enough to say, if we say it cancels, we know what we mean. Okay, so the 4 divided by 4. Now I've changed this by fourthing it. So I'm going to change this side by doing the same operation. And so if I do that, what I end up getting is, oh, just the x left all by itself. Keep our equal sign where it is. 28 divided by 4 is 7. Okay, so I've worked towards getting x by itself. I think I see how I do this. I need to use opposite operations, or I can add, subtract, multiply, and divide anything I want to on the left side, as long as I do it on the right side. And we should be able to work our way by undoing these operations. Now, and then a deeper question, or more serious question, is how did I know what order to do this in? Some people just instinctually look at this and they know which order they want to work in. They know they want to start with the 15, but why? So you know the order of operations. It tells you, the please excuse my dear Aunt Sally thing, which is misleading. But if you look at this, doing a subtraction should definitely be behind a multiplication. Why is that? Well, I want to ask you a question. You get dressed every day. What do you put on first, your underwear or your pants, shorts, whatever you're wearing? Usually your underwear first, right? and then your shoes. No, well, underwear, then your pants, then your shoes. When you go to get undressed, do you undress in the same order? Do you take off your underwear first, then your pants, and then your shoes? No, to undo something, you kind of go in backwards order, right? Depending on how baggy your pants are and what shoe size you have, it might be really hard to get your pants off over your shoes. So you undo this in the backwards order. Well, that's kind of what we're working with here, solving. Typically, I would, if this were like a 1 or a 2 or something, I could just do order of operations. I would do times 4 first, and then I would subtract 15. But since I am unraveling these things from this side, I work backwards order. I get rid of the minus 15 first, and then get rid of the times 4 first. Another way of thinking about this is we're going to simplify these down so that they almost always look in this form at the end before we go to do our solving. And so you could always work further away from x and work your way into x, just as a simple way of explaining that. Okay? Now, so I think we kind of have that figured out. But before we really dive deeply into it, I want to tell you that my kind of technique for solving equations is based off of like this order of things to do. I call it my triple S. 1, 2, 3. And the first, actually, I'll go ahead and spoil it. We don't actually solve anything until the last S. Solve. Okay. This is where we finally get to solving. Finally. Oops. That's not what I meant. Let's try that. Finally. Okay, well, what are we doing first then? Well, I'll go ahead and tell you, the first thing we're going to do is we're going to simplify each side. Oh, our last lesson was on simplifying, so it was really nice to build that skill. So we're going to look at the left side of the equal sign, and we're going to simplify that. And then we're going to look at the right side and simplify that. We're not crossing anything over the equal sign yet. We're just working on the left, working on the right, and then we're ready to mosey on. The next thing we're going to look at is to see if our variable that we're solving for is on the same side. So if I have an x over here and an x over here, and I want to get x all by itself, I need to get them together. I can't have x's on both sides and solve for x. So we'll learn how to do these things when we get there. And then finally, the last step is to actually, do our solving. So my triple S, simplify, same side, solve. Okay, so let's look at some examples. Now, we've already done a really simple example to start with, so let's go ahead and skip some of the really simple stuff, and let's start with something like this. 2x plus 10 equals 5x minus 2. So if I look at the left side, so completely ignore the right side for a second. 2x plus 10, do you see anything to simplify? Do you see any? Remember what simplify was, DC. Do you see any parentheses to distribute over here? And I say, no, there's nothing to distribute. Do you see any like terms to combine? No, 2x and 10 are not like. So this whole left side has been simplified. It already is simplified. How about the right side? Do you see any parentheses to distribute? No, I don't see any. Do you see any like terms to combine? No, I don't see any like terms. All right, well, if we're following these 3 S's, we've already done the simplify both sides, or it came simplified. Yay, that was easy. Now, are the x's on the same side? Uh-oh, I have an x term on the left and an x term on the right. You might feel a little bit panically. Okay, well, how do I handle this? Well, what I'm going to do is do the same thing I would have done with something like if I told you to get rid of this plus 10. You would have said, oh, plus 10, to get rid of that, I would minus 10. Or you see this minus 2. How would I get rid of that? I would add 2. So if I'd like to get rid of an entire term, it doesn't matter which I work with. I'll probably get rid of the smaller one every time, just to avoid negatives for at least one more step. So this is, what, a positive or a negative 2x? Well, look out front. There's no sign, so that means it's a positive 2x. Well, how do I get rid of a positive 2x? I could subtract 2x. Now I am changing the value of this left-hand side, so I need to change the value of the right-hand side by the same amount. So I am subtracting 2x. I may want to erase this little bar here so it doesn't look like I'm dividing. There we go. So I am subtracting 2x from both sides. Okay, so it's staying equal. Now notice I could line this up anywhere I want, but since this 2x is going to be the same, it's the same term as the 5x, I'm going to want to combine those. So 2x minus 2x, gone. What am I left with over here is just a positive 10. I'm not going to bother putting the plus sign, but you could leave it if you wanted to have no it's a positive 10. 5x minus 2x, we already know how to combine like terms from last lesson. That is 3x. And bring down your minus 2. So now I don't have x's on both sides. They've been put together, so that's taken care of. Which just leads me to solve, which is exactly like the last problem we did. Except for the x is on this side, but it works the same way. Is the x by itself? No, what's it get with it? A 3 and a minus 2. Which piece do I get rid of first? The minus 2. So I'm going to add 2 to get rid of a minus 2. So that means I'd add 2 to both sides because I'm changing the value. Now, minus 2 plus 2 is gone, or it's 0. 10 plus 2 is 12. 12 equals 3x. Is x by itself yet? No, it's got this 3 with it. That's 3 times. How do I get rid of 3 times? I divide by 3. Now, because I'm changing the value of this side, I got to change the value in the same way on the left side. 12 divided by 3 is 4. 3 divided by 3 divides to 1, or we can lazily say cancels, leaving us with just x. So x equals 4. We've solved for it. Now I'll go ahead and tell you the really fun thing. So we did the last step solving. The really fun thing about solving is you can always go back and check that your answer is correct by plugging it into the original equation everywhere you see an x and checking if it is in fact equal or balanced. Let's do it in our heads. 2 times 4 is 8. 8 plus 10 is 18. Check. 5 times 4 is 20. 20 minus 2 is 18. 18 equals 18. So yeah, this is in fact the true answer. You can always just quickly check to be sure you have it correctly. Let's do a few more examples then. What if I give you one that's not too hard but causes a lot of people to panic? Let's go something like this. 2 over 5x equals 6. All right. Well, I look at this and I'm thinking, oh my goodness, I really don't like that fraction. So let's see if we can hit up our 3 s's. So is there anything to simplify? Do you see anything to distribute or any like terms? No, there's only one term. How about on this side? No, it's just a single number. So it's simplified on both sides. All right, well, do I need to worry about x's on both sides, getting them together? No, the x is already on the same side. So then I get to solving. I say, oh my goodness, can I take care of this? And the answer is, yeah, it's not too hard. I have a 2 and a divided by 5. I could get rid of both of these at the same time, or I could take my time and get rid of one at a time. In the order of operations, multiplication and division are of the same level of importance, so I could get rid of either of these first. Let's get rid of the part that's bothering you. This is a divided by 5. How do you think I get rid of a divided by 5? I'm just going to multiply both sides by 5. Because what will happen is I'll have a 5 on the top and a 5 on the bottom, and they will divide to 1 or cancel out, leaving me with a 2 and an x. Or, to put it simply, a 2x. Now, 6 times 5 is 30. Okay, this looks much easier to work with. I feel a whole lot less panicky. If I want to get rid of that 2, I can divide both sides by 2. And now x is equal to 30 divided by 2 is 15. Awesome, that wasn't very hard. So now we've solved it, and you could plug it in and check if you wanted to. All right. Now, let's keep moseying and do some more examples. Let's start building more. Let's do some that actually require us to look at more of those s's, all 3 s's. Let's go with 2 parentheses, x minus 5 plus 3x equals 4 parentheses, 3 plus 2x. And if I'm trying to do this, I know I have my 3 s's I need to tackle. And the first one's to simplify, and it definitely looks like I have stuff to simplify this time. I got stuff to distribute. I should have some like terms. So let's take care of the left side here. Let's distribute first. 2 times x is 2x. 2 times a minus 5. This is what we did last lesson, simplifying. So you should be pretty smooth on this. 2 times a minus 5 is a minus 10. 2 times a negative 5 is negative 10. And let's bring down this plus 3x. Now, I have like terms, 2x plus 3x, that gives me 5x, and bring down the minus 10. Now, I have not changed any values on this side. I have only simplified. I've combined and distributed and multiplied stuff that was already there. I didn't add any extra operations in, but I've made it look a whole lot more easy to work with. So we want to do that to the other side as well. This one has some distributing. 4 times 3 is 12, and 4 times 2x is a positive 8x. And now there's no like terms to combine, so I can just bring this on down. 12 plus 8x on down. So we've simplified both sides. Now I need to get the x on the same side. That's this next one. So I have a 5x and an 8x. I always like to go and move the smaller of the two. Look out front. Is this a positive or a negative 5x? It's a positive 5x. So to get rid of a positive 5x, I subtract it from both sides. So I'm left with a negative 10 is equal to 12. Let's see, 8x minus 5x. That'll leave me with 3x. Nice. All right, and we can keep working here. So we've gotten the x's on the same side. Now we need to solve. Is x by itself? No. What's with it? A 12 and a 3. This is a positive 12. How do I get rid of a positive 12? I subtract 12 from both sides. Negative 10 minus 12, that's negative 22. And I'm left with 3x. All right, almost finished. But x is not by itself. It still has a 3 multiplied by it, so we'll divide both sides by 3. Negative 22 divided by 3. Oh my, that's just a nasty fraction, and it doesn't reduce any. So guess what? In this course, let's leave everything as reduced fractions. That's much easier. You don't even have to reach for a calculator. You know that's nasty. It doesn't simplify. Leave it as is. Negative 22 over 3. And that's the right answer. I've done this. If you wanted to go plug it in and check it, you could. You probably want a calculator with this nasty fraction, but it's okay to get fractions. A few more examples. Let's do another one like that one. That's a little more like busy. That has us do all these 3 s's. That has us simplify both sides, get the x together, and solve. One more for practice, and then we'll move on to a few other things. So we'll go with 3 parentheses x plus 5 close parentheses minus 2. And we'll say that's equal to 6 minus parentheses x minus 5. And this is trying to be sneaky and evil here because you have a subtraction sign with no number. So I'm going to go ahead and put in that understood 1 so I know what I'm distributing there. Makes life simpler. So let's go ahead and doing these 3 s's, we're going to simplify both sides. So I need to distribute here. So 3x plus 15. Bring down this minus 2. Let's see, 3x doesn't have any like terms, so I'm going to bring it down, but positive 15 minus 2 are their like terms, so that'll give me positive 13. Nice. So now let's do this other side. Bring down the 6, but I need to distribute this negative 1. So I'll become negative x, and negative 1 times negative 5 makes positive 5. All right, and if I'm looking at like terms, 6 plus 5, these are like terms, 6 plus 5, so that'll be 11 minus x. Nice. Now, we've gotten everything simplified. Now I need to get the x's on the same side, and I have an x on both sides. So let's look at the smaller one, and negative x. To get rid of a minus x, I'm going to add x to both sides. 3x plus x is 4x, and we can bring down the everything else. So now, we're almost there. Let's start the solving part. We've got them on the same side. We'll start solving. So get rid of the 13. So minus 13 minus 13. So 4x is equal to 11 minus 13. Well, that is just negative 2. And then we're almost done. Is x by itself? No, I got to divide by 4. Ooh, once again, it looks like we're getting a fractional answer. Negative 2 over 4. So we've solved. Now, I'll go ahead and tell you, in this course, we would like to make sure we reduce any fraction we get. Negative 2 over 4. Does anybody know what that reduces to? Negative 1/2. Okay. All right. Awesome. 2 more solving examples, and then we'll talk about a same but slightly different topic. So, what if I were to give you something like this? X plus 0.07x is equal to 4.28. Huh. I want to talk about two ways to do this thing. So I'm going to copy it over again beside it, and we'll work this two different ways. And you can do whichever is your favorite, but it just kind of philosophically discusses some important ideas. Is there anything wrong with trying to work with this in decimals? No. I could just go and use my calculator and kind of chug along here. What number is understood to be in front of this x? Because it's not showing. I think that'll make this problem easier is to show this number. So 1x plus 0.07x. So I do have like terms to combine. If I'm hitting my three s's, if I'm trying to simplify, there's nothing to simplify on this side, but I do have like terms here. 1x plus 0.07x. A lot of people struggle with this, but it's 1.07x. When you're adding like $1.07, you have $1.07. And then you're like, okay, well, this looks nasty, but all right, I'd like to divide both sides by 1.07 because it's what's being multiplied by x. And then you'll definitely want to reach for a calculator unless you know that off the top of your head. I can do this in my head because I've done a lot of math in my life, but I know that's going to be 4. But you may feel really queasy carrying these decimals all the way through. So I want to talk with you about another idea. So this thing has 2 decimal places. This thing has 2 decimal places. Let's go ahead and add the 1 here so that we have it. So there's one idea that, okay, well, I'm allowed to do anything I want to as long as I do it to both sides. What if I were to get rid of this by making the decimal go back twice? Well, to do that, that's the same thing as multiplying by 100. So I'm going to multiply both sides by 100, or I'm going to move the decimal back twice. So let's see, 100 times x, that'd be 100x. 0.07 times 100 would be 7x. And 428 times 100, or 4.28, would be 428. All multiplying by 100 does is move the decimal twice. Well, this is larger numbers, but it's actually not hard. 100x plus 7x is 107x. That's equal to 428. And then I would just need to divide by 107. Oh, x equals 428 by 107 is 4. So I do get the same answer no matter which way I did it. But one of them may appeal to you more than the other, so just feel free. This multiplication trick here is a trick that helps people get out of stressful situations, whether there's fractions or decimals. It makes people's life a lot happier than having to deal with the decimals or fractions, especially if there's no calculator around. We might could have done this without a calculator. This, you might have gotten queasy if you don't remember your long division. Okay. So let's look at another one that can rely on a similar trick. That was decimals. What if I have fractions that make me feel unhappy? Like 2. Let's write it this way, but 2/3 x, or 2x over 3, plus x over 2 is equal to 7. Is there anything wrong with trying to work this as is? No, you can work it as is. If you're really good at adding fractions, 2/3 plus a half, you would have to figure out what that is and have that fraction times x, and then you could solve it. But a lot of people look at this, especially if there's a lot of fractions going on, and they feel almost sick to their stomachs. They do not like seeing these fractions. Well, let's use the same trick. I don't like these fractions, so I could try to get rid of one at a time, and you could say, okay, well, what's on the bottom of this one? Divided by 3. How do I get rid of a divided by 3? I multiply by 3, so I would need to multiply both sides by 3. What's that going to give you? 3 times, well, if I put a 3 in there and a 3 here, let's distribute that 3. These are going to cancel, and that's just going to leave me with 3x over there. That's a bit sloppy. Let me undo that writing, but that's what's happening. As I'm multiplying a 3 here, it's going to cancel. So I'll be left with 2x plus, and I bring a 3 here, it's not going to cancel with a 2, so that leaves me with 3x over 2. And a 7 times 3 is a 21. Part of this to understand is anytime you multiply a whole number by a fraction, it's multiplying to the top of the fraction. Okay, so this 3 is going to the top of both of these fractions. And when this 3 comes here, we get like 6. 6 divided by 3 is 2. Or you could think of it as the 3 is canceling. Now, I got rid of one of my fractional problems, but I still have another one. So let's just do the same trick again. Let's multiply both sides by what's on the bottom here, 2. Multiply both sides by 2. Well, 2 times 2x, that's simple, that's 4x. And when I multiply the 2 here, it's going to just cancel with that one, leaving me with 3x. And 21 times 2 is 42. All right, nice. Now we finally can, we've done some killing off of fractions. We can do our triple S. We can simplify. 4x plus 3x is 7x. Don't have to worry about getting x on the same side. We can now solve. Well, that's an easy solve. All I gotta do is divide by 7 on both sides, and x is equal to 6. That's really easy. So what I'm trying to show here with these last two examples is that if you have fractions or you have decimals and you don't want to deal with them before you hit your triple S, you can kill them off. Kill off the fractions and vegetables, fractions and decimals. That will make it much easier to solve equations. Okay. Now I have two other examples I want to show you. And sometimes when I teach this class in person, I have fun just giving these. Like, okay, y'all feel good now? We've worked all these examples. Here, try this one. And it's a bit evil for me to turn people loose on this example when we haven't talked about what's going to happen. But it really makes a point. So let's just go about doing this together. I'm not going to write my 3 S's. At some point, you should start memorizing those. We need to start with simplifying. So I need to distribute this 2. So the 2 times 3x is 6x, and 2 times 2 is 4. We're going to bring down this side. All right, now I got this x on each side, so I'm going to try to get rid of one of them. So I'm going to subtract 6x to get them on the same side. And oh no, what happened? 6x minus 6x is gone. I'm left with just 4. Oh no, 6x minus 6x is gone. I'm left with just 4. Both x's are gone. Or basically, I could say all my variables, they've disappeared on me. Okay? When your x's are gone, this is a special case. All right, and there's two special cases, two of them. Okay? One special case is that no matter what x value you plug in, you will get a true statement. So that basically means everything and anything you plug in is true. So everything and anything is a solution. So we call that many solutions or infinitely many solutions, or you could say x's solution is the most proper thing is we call this all real numbers. So what's the solution set? It's every real number. How do I tell when I have this one? Well, whenever you're left with a true statement. This is true. Last time I checked, 4 equals 4. So that means that my answer, what I'm going to write down for my answer is all real numbers. X can be all real numbers. If you'd like some lazy shorthand, the mathematical symbols for all real numbers are upside down A and an extra bar on your capital R. This weird scripted R means real numbers. This means in all cases or all of them. All real numbers. So there's the lazy shorthand for that answer. Let's look at another example then. What's the other case? That was one of them, all real numbers. What's the other case? Well, let's see here. We'll be lazy and have the same left-hand side as the last problem. And I'll have 6x plus 5 over here. So we go about our business. 2 times 3x is 6x, and 2 times 2 is 4. Okay, I've simplified. Now I have an x on each side, so let's get rid of one of the side's x's. And oh no, it happened again. Both x's cancel, and I have 4 equals 5. Now, this is a special case then, because my x's are gone. Once the x's are gone, it's a special case. Look at this. Does 4 equal 5? No, this is not true. This is false. And so when you have a false statement, what it's telling you is that nothing will work. There is no solution. No matter what x value you plug in, you will not get an answer. The shorthand for that is you can write a 0 with a slash through it if you wanted to be lazy and be like a mathematician. So this means no matter what x you try to plug in, you're never going to find anything to make this equation true. There is no solution. There is nothing to make it work. Okay? And so usually we end up with a nice answer. Usually we go back to all these examples. We can work things and get x equals 4, x equals negative a half, or x equals for, but sometimes there's special cases where if your x's cancel out or disappear completely from the problem, it's either going to be all the numbers or no numbers, no solutions. Okay? So, but that's all I have for you today. I'll see you next time.